Okay, good evening, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione. I'm the interim director of NITheCS. Before I introduce the speaker, I would just like to invite you to join the NITheCS mailing list so that we can always send you the announcements of talks like this. Yeah, usually our talks are in the NILSI at 4 p.m., but today there was unfortunately some other event there and we had to find, thanks to Professor Janelica, an alternative solution for a venue for the colloquium. Today's speaker is Dr. Cerene Rathilal, and we're very happy to have her here today. Cerene recently joined UKZN as a senior lecturer. No, as a lecturer. So, but she deserves the promotion, so we will make a plan. Cerene is working mainly in algebra and topology, and the title sort of gives that away. Yeah, and she's very, very active in various engagement activities. Yeah, for instance, a few weeks ago, we hosted here in Stellenbosch the STEM Mentor Initiative that in the meantime already took place in Johannesburg and at UKZN, I think.
It's starting at
Okay, it's starting at UKZN very soon. She's also very active in the Center of Excellence for Mathematics and Statistical Sciences, and probably many other things that I've forgotten now. So, Cerene, we're very happy that you're here today, and you're most welcome to start with your presentation. Thank you very much.
Thank you. Okay, good afternoon, everyone. Firstly, I want to say thank you to everyone for making it out here. I know there was a change in time as well as venue, but I also want to thank NITheCS for giving me the opportunity to present a colloquium talk, as well as Professor Janelica for hosting me this week at Stellenbosch University on a research visit. So today I'm going to be talking to you about sublocales. But the true motivation for the work that I'm going to present comes from property S. So property S is a property that is attributed to Sierpinski. And that is why it's labeled property S, because of his name. It is essentially a concept that has been defined in metric spaces that captures a notion of connectedness. The idea is that if I give you an epsilon, then you would be able to find a finite collection of connected subsets of the metric space whose diameter would each be less than epsilon, such that the union of those connected sets would give you back the entire metric space. So that is what property S does. So later on in metric space theory, in frame theory, after metric frames came to prominence due to work by Professor Poulter, Isbell, and many mathematicians, my supervisor, Professor Babelwal, had taken this notion of property S and then studied it in metric frames as well as uniform frames. The aim of today's talk is for me to take this concept of property S, which is now defined and well established in the theory of frames, but to actually characterize it in terms of sublocales, which are generalized subspaces. And that will be the goal at the end of this talk. This work has actually emerged from the work that I did in my PhD. It was quickly forgotten because I got on with other work and I actually never presented it. So when I was invited to do this colloquium, I thought, well, why not talk about property S? So to begin, we're going to be talking about a structure called a frame. But before we get there are a few other ingredients that we're going to need to recap on. The first of which is that we need to recall what is a poset. So a poset is a set that is equipped with a partial order, meaning that the operation on, the ordering on the set is essentially reflexive, anti-symmetric, as well as transitive. So that's what it means for a set equipped with the partial order to be a poset. Well, we call that a poset. If in addition, we have that for any two elements, you can find the meet, meaning the infimum, then we will refer to this poset as a meet semilattice. If you also find that for any two elements, you can find the join, then this poset can be called a join semilattice. And if you have that both those properties are being satisfied, both joins and meets live in your set, then we refer to that poset as a lattice. Now, for the purpose of understanding frames, we need the concept of a complete lattice. A complete lattice is a lattice for which whenever you take a subset, you would be able to find the join of that subset, and it will itself now live. Well, the lattice is closed under arbitrary joins. That is essentially what is being said. Or equivalently, in a complete lattice, if one can find arbitrary joins, if they exist, then so will the arbitrary meet. So this is our notion of a complete lattice. Now we come to frame. A frame is a complete lattice. It is a complete lattice that satisfies an infinite distributivity law, meaning that we have binary meets distribute over arbitrary joins. Here it's distributing over a subset of the frame L. That's what's happened. Now, in particular, if we look at this definition of a complete lattice, we see that for any subset, the join exists. So, and similarly, for any subset, the meet exists. So that means that the empty meet and the empty join exists. And since the empty meet and the empty join exists, that means we could have a top and a bottom element of your complete lattice. So utilizing that understanding, we can then denote the top element of the frame by 1 and the bottom by 0. If we're referring to more than one frame, then that's when we start to use subscripts to denote which frame we're referring to. So how is this algebraic structure now related to topology? So it turns out that if you consider a topological space, and if you consider all of the open subsets of that space, then that equipped with subset inclusion is actually a complete lattice. And so we refer to that collection of all of the open subsets as the frame of open sets of a topological space. And by now using this algebraic approach to study topology, you now see that instead of talking about, well, essentially what we're doing is we're working with the open sets rather than working with the points. So by not talking about the points, this is where the name point-free topology comes from. So when one works with the objects of frames, or sometimes you may come across the language locale, the term locale, then we are essentially working in the realm of point-free topology when we're trying to make conclusions, topological conclusions using algebraic approaches. Now, today I want to talk about generalized subspaces. And in order for us to get there, we're going to need the concept of an hating operation. Now, we know that a frame has an infinite distributivity property in which it preserves arbitrary joins. So, well, maybe before I use that explanation, let's look at the definition of what is a hating operation. A hating operation is a binary operation denoted by an arrow. What does it do? It does the following. Well, whenever you have 3 elements in the frame such that C is less than or equal to A arrow B, C less than or equal to A arrow B happens if and only if C meet A is less than or equal to B. So this arrow is called the hating operation on the frame. And actually, these are Galois adjunctions. So if I had a frame, and if I take an element X, then I can map it to X meets some other element B. And because I'm in a frame, it means that that map which just sends X to X meet B, would preserve arbitrary joins. And when that happens, well, that is actually, when you learn about Galois adjunctions, that's the left adjoint. It is a map that preserves your arbitrary joins. And the right adjoint of that is actually the Hating operation, or the Hating algebra. So for the purpose of understanding sublocales and being able to characterize them or define them, we will require this notion, this Galois adjunction of the Hating operation. Fun fact, every complete Hating algebra is also a frame. That is also something that one could check if you are keen on studying Hating algebras. Now, in particular, because we are working with a right adjoint, because the Hating operation is a right adjoint, it will preserve arbitrary meets, and that's the property you're seeing here in H5. But in addition, I'm going to point out H4 because you kind of have a property that has join and meet distributivity, even though the operation has now flipped. Okay, so let's talk about sublocales. What is a sublocale? These are indeed supposed to be generalized subspaces. So we define a sublocale to be a subset of a frame that satisfies two conditions. The first of which is that your subset must be closed under arbitrary meets. The second is that whenever you take an X and L and any element S from the subset of the frame, then X arrow S would itself live in the subset. If these two properties are satisfied, then we refer to the subset as a sublocale. One can also characterize sublocales in other ways, and I will point out an alternative way shortly. But one could also think about it in terms of embeddings, localic embeddings, where one would want to embed a subset of a frame back into a frame. And that could be another approach. But now let's consider this definition that we have. In particular, we see that sublocales will always be non-empty. Why is that the case? Because the meet of the empty set belongs in S. And therefore, every sublocale will contain the top element of the frame. You also observe that the meet, since we work with arbitrary meets, the meet in the sublocale is exactly the meet in the frame L. And in fact, the meets turn out to be intersections when you're working with the collection of all of the sublocales. But in general, joins aren't that well behaved. So the join in the sublocale need not be the join from the frame. So if you're working with your collection of sublocales, then it turns out that that collection will itself be a complete lattice under subset inclusion. We shall denote this by S of L. The collection of all sublocales of L will be denoted by S of L. And in particular, the join of the sublocales need not be the union, as you might have expected it to be. But in fact, the join of all the sublocales is defined in the following way, that it consists of the meet of all subsets, where the subset, well, the set comes from the union of all of the sublocales under consideration. So this is how one thinks about the sublocales, sorry, the join of the sublocales. Yeah, I wanted to draw some pictures, which I omitted to do, but to give you some intuition, I guess, a bit about how sublocales behave. Let's see. So if this is L, okay, it's a very bad drawing, and it has a top element. So the sublocale, again, still has that top element, but you can think of it as something like that. So this would be a sublocale of your frame L, where it still has that top element. Well, the top element of L is the top element of S. Now, this type of picture and this intuition comes in handy when one thinks about open and closed sublocales, which I will point out shortly. But I just thought that it might be necessary to include that there. Okay. Now, if we consider this complete lattice, which consists of all of the sublocales of a frame, one may want to ask whether that collection, that complete lattice satisfies the frame property, meaning does that give you back a frame? Well, it doesn't, it turns out. But in order for me to explain that, well, the infinite distributivity property that I mentioned to you earlier had finite means distribute over arbitrary join. So we also have another notion called the co-frame property, where we instead have the binary join distribute over arbitrary meets. So this is a co-frame property. So it turns out that the collection of all of the sublocales does not satisfy the frame property. It satisfies the co-frame property. And so therefore we refer to SL as a co-frame. Now, I did mention that there are different ways to kind of describe sublocales, and another approach is to use a nucleus of a frame. I'm going to introduce this notion because I'm going to utilize it when I end up talking about diameters and sublocales. It's actually very central to how one would define a metric structure on a sublocale. So what is a nucleus? A nucleus is simply a map from your frame into your frame satisfying 4 axioms. The first of which is that for any element in the frame, A will be less than or equal to the nucleus of that element. The second of which is that the nucleus map is order preserving. Thirdly, we have that the nucleus map is idempotent. And the fourth condition says that the nucleus map preserves binary means. So it turns out that we have a one-to-one correspondence between sublocales and, well, a nucleus. So if I give you a sublocale, how can you define a nucleus mapping? Well, you can do it by saying the following, that we will define a map from L into L that sends every element from L, every A in L, to the meet of all S's from the sublocale that we've begun with, such that S was bigger than or equal to A. So that constitutes a map that satisfies N1 to N4. The reverse, if I give you a nucleus map, how can you recover, or how can you now get a sublocale? Well, it's simple. You simply take the image of the frame under that map, and one can then check that what you get back is indeed a sublocale. So for now, I'm going to move away from this connection between sublocales and nuclei, but I'm going to revisit utilizing, or how does one get a nucleus from a sublocale in the few slides to come. So let's talk about open and closed sublocales. Well, we do have these notions even when talking about generalized subspaces. An open sublocale is defined as follows. If you have a frame, the open sublocale of any element A in the frame is defined to be the collection of all X's such that A arrow X coincides with X. We then have a notion of a closed sublocale, which is simply the upset of any A in your frame. So one has to now check, do these definitions give you back sublocales? They do, and I've got that on the next slide. There is an alternative way, which is sometimes computationally more feasible to look at or work with open sublocales, and that's stated below. But more importantly, once you know that these two things are indeed sublocales, you can end up seeing that, well, intuitively, you would be able to see that they're actually complements of one another in the co-frame, meaning the collection of all of the sublocales. But moreover, this open sublocale operation in here is actually one-to-one. So whenever you have OX equals to OY, one can conclude that X equals to Y. To check that OA is indeed a sublocale, well, it's a very routine process where you first have to check that it's closed under arbitrary meets and that the hating operation property is satisfied. And in order to do that, actually, we needed a lot of the hating operation properties that was listed in the earlier proposition from the earlier slide. Showing that up arrow A is a sublocale is significantly easier. But then the next question that arises is, because I know in particular that the collection of all sublocales of a frame is not a frame, it is a coframe, are there any instances under which the frame property actually holds? The answer to that is yes. So proposition 1 is actually listing two situations under which finite meets, in this case intersections, distribute over arbitrary joints pertaining to sublocales. This is actually quite a well-known property, although it's not really recorded in the literature. But if one has to talk to frame theorists, they accept that this is always true. And so I then set out to write out proofs for that. Proposition 2 is not listed anywhere. And this was something that I had then come up with. And so proposition 2 says the following, that if you have a frame and if you have a sublocale, then the frame property is satisfied in the following condition when, well, in the following way, such that that sublocale S will distribute over an arbitrary join of open sublocales where the AIs for those open sublocales come from the frame. So here we see that the frame property is actually being preserved when one is considering the case of working with open sublocales. Well, the proof to that wasn't too difficult. One merely needs to observe that open sublocales preserve arbitrary joins, so I could push that in. Then considering what this actually means, what does it mean if I'm working with the set S intersected with the open sublocale about the join? Well, that simply means that I'm working with all X's from S, satisfying that open sublocale, the hating property. So that's what's written here. But then earlier we saw that the hating arrow has a join meet distributivity. And that's what's happened in here, where we now have that the join of with the arbitrary join, arrow X, can now be expressed as the arbitrary meet of the arrows. And we get the last equality by noticing that AI arrow X actually lives in S intersection of OAI for every I, and then that equality would follow. So that was easy to show. Well, then utilizing proposition 2, which you just saw, one can prove the following when comparing families of sublocales. So let's suppose you have an arbitrary family of sublocales indexed by set I, and you have another family of open sublocales indexed by the same set. And you know the following 3 things, that the join of each of these families coincide, that for any 2 sublocales that you pick from the first family, its intersection will have to be trivial. And lastly, that for each I, the open sublocale is contained in the SI. Well, then it is true that SI will actually equal to the open sublocale at AI for every I. Of course, in order to prove this, one needs only check that SI is contained in the open sublocale of AI. And so that is what proceeds in the following proof. Okay. I'm now going to talk about connected sublocales. So connectedness is a property that, well, is well studied in frames. And what does it mean for an element to be connected in a frame? Well, an element of a frame is connected if, whenever, that element is expressed as the join of 2 elements whose meet is disjoint, whose meet is 0, then it must be the case that either B is the bottom element of the frame or C is the bottom element of the frame. We then say that a frame is connected if the top element of the frame is also connected. So if one regards a sublocale as a frame, then one can define a sublocale to be connected if the top element of the sublocale is connected with respect to the operations, with respect to the join in the sublocale itself. And so that's what I've stated here as per this definition. A sublocale is connected if and only if, whenever the top element is expressed as A join B, and then what needs to be clear here is that the join we're referring to is the join from the sublocale. And we have that A meet B is the bottom of the sublocale, then it must be the case that the A is either the bottom or B is the bottom. Then in a very important book in frame theory published by Poulter and Piccardo called Frames and Locales, they had extensively studied connectedness of sublocales. And they had provided some characterizations. So the statements that you see on this slide has a minor modification to the statements that were listed in that book. So the modification corrects an error in here, and therefore I had to rewrite the proofs. But if you read the book, you don't have to be alarmed, because any results that they put in the book will still be true. You would just have to go and modify all of the proofs once again. So what is the statement for a sublocale to be connected? Well, we can characterize it in terms of closed sublocales and open sublocales. So a sublocale is connected if whenever that sublocale is contained in the join of two closed sublocales whose intersection, the same thing, with themselves as well as S is trivial. So whenever that happens, it must be the case that up A intersection S is also trivial, or up B intersection S is trivial. So one of the two. We can then replace that formulation by replacing all closed sublocales by open sublocales, and that is in fact still going to hold true. There are some other really nice properties that one can obtain about sublocales. So for example, if you have a family of sublocales, an arbitrary family of sublocales, and for any two sublocales you pick, if you see that they meet non-trivially, then it must be the case that the join of all of the sublocales will be connected. So of course I meant that the collection we started with is connected. And also in Poulter and Piccardo's book, they include the following property, which is easy to check, that if you have a family of connected sublocales whose intersection is non-trivial, then the join will then be connected. So I've taken us through looking at various concepts that are all going to converge to one part. I mentioned at the beginning that I want to talk about property S. Property S can only be defined on a structure that has a metric. So in order for me to talk about property S on frames, I'm going to now need to tell you what is a metric frame. A metric frame is a frame equipped with a diameter function, right? So this diameter function is a map from L into the extended reals. It satisfies 6 conditions. The first 4 of which, when satisfied, defines what we refer to as a diameter. So M1 says that D maps the bottom element of the frame to 0. The second axiom says that D is order preserving. The third says that whenever you have A meet B is not the bottom, then the diameter of the join is less than or equal to the diameter of the sum of the 2 elements. And M4 is a property about covers. It essentially tells you that if you consider the collection of all elements whose diameter is less than epsilon, then the join of that set must give you the top element of the frame. If in addition to M1 to M4, M5 is also satisfied, then we refer to this diameter as compatible. And as you can see, we have quite an extensive axiom that needs to be satisfied. M6 tells you when the compatible diameter will then be considered a metric one. And here we say that the diameter will be a metric diameter if for any element in the frame whose diameter is finite and epsilon greater than 0, you would be able to find two other elements that are smaller than A, such that the diameter of those two elements are less than epsilon, and it satisfies that inequality. So L equipped with this function D, satisfying M1 to M6, is then called a metric frame. So we now have a notion of a metric structure on a frame. And now, considering the fact that we've looked at generalized subspaces and sublocales, the question is, how does one now define a metric structure on a sublocale such that it is inherited from the original metric structure? Well, we do that using the nucleus. So we had seen earlier that if I give you a sublocale, you would be able to define a nucleus in the following way. And we are going to utilize this definition extensively in order to understand metrics on a sublocale. So if you're given a frame and a sublocale S, the question is, how does one define a metric on S that is induced by D? Well, we do it in the following way. We define ds, which is now going to be the metric diameter on the sublocale, by taking the infimum of all the D diameters. So the infimum of D of A, where D of A is the metric diameter from the original frame, such that the nucleus evaluated at that element is bigger than or equal to B. One can check that D of S is in fact a metric diameter when you regard S itself as a frame. So S equipped with DS becomes a metric frame. And so utilizing that, well, the first step is to check, is this definition well defined? Well, it is, but that comes with a lot of checking, because you might be in a situation where you have S as a sublocale. Well, S and T are sublocales of L, where S is a sublocale of T. The question is, will the diameter on S induced by L coincide with the diameter on S induced by T? And it turns out that it does happen. That takes some checking, and that's what theorem 6 is actually highlighting in here. And that's what the preamble was setting up, so that we would understand the difference between ds and rho s. So ds in here is what I defined to be the diameter on S that is induced from L. And I then defined or denoted rho S. Rho S simply denotes the diameter on S that is induced by T. And one can check that those two things will always coincide for any element A in the sublocale. Well, if we're now talking about diameters of elements in a sublocale, what about the diameter of the sublocale itself? The intuition behind this is that diameter maps are order preserving. So that means the top element of the frame or the sublocale will have the largest diameter or distance. And so we naturally define the diameter of the sublocale to actually be the diameter of the top element when calculated using ds, meaning the diameter on S induced from L. And so I've just written out the full definition in there. So some really nice results emerge from this. The first of which is that if you have any element in the frame, one can just consider the open sublocale of A. And the diameter of the open sublocale using this definition actually coincides with simply the D diameter of the element A, something that I found really interesting. Moreover, if you have S as a sublocale of T, then as you would expect, the diameter of S is less than or equal to the diameter of T. And we also have a property with respect to joins when you have two sublocales S and T which meet non-trivially, then the diameter of the join is less than or equal to the sum of the diameters. All right. I'm now going to point out something about the closure, which is going to be relevant for our last result. And so, as you would expect in topological spaces, the closure of a subset is the least closed subset that contains S itself. So using that same intuition, one can define the closure of a sublocale, and we define the closure of a sublocale to simply be the upset of the meet of S, because the least element in the sublocale is the meet of S. If I take the upset of that, I'm essentially now ensuring that I would be able to capture everything in it. So the question is the diameter of the sublocale S equal to the diameter of the closure of the sublocale? And that is indeed true. But of course, in order to prove that, we're going to have to consider the two diameters that one could obtain. The first of which will be the diameter on S induced by L, and the second of which will be the diameter on S closure induced by L. We would want to check that those two diameters coincide everywhere. This was a highly non-trivial proof, but it works out well. And as a corollary, one can now conclude that therefore the diameter of S equals to the diameter of S closure. Okay, property S. So I did mention the definition of property S in metric spaces at the beginning. In frames, it amounts to saying the following, that if I give you any epsilon greater than 0, then your frame has property S, amounts to saying that there would exist a finite collection of connected elements whose join is the top, meaning that that finite collection of elements is a cover of the frame, as well as that collection is, I did mention, is connected, but the diameter of each of those connected elements is less than epsilon. Now, the aim here is to characterize property S, but now in the language of sublocales, no longer just using elements of frames. That's what I've set out to do. So firstly, even without using property S and just using the metric properties on a frame, we can conclude by proposition 12 that if you have a metric frame, and if I give you any epsilon greater than 0, then you would always be able to find a finite collection, an arbitrary collection of open sublocales whose diameter, the diameter we just defined, would be less than epsilon, and such that the join of all of those sublocales gives you back the entire frame. The proof of which, well, I could go through this. So if we let epsilon be greater than 0, then we know by the metric frame axioms that UD epsilon is a cover of the frame. And so I now have that set. But in particular, if I take every element from that cover, I could then form an open sublocale about every element in that frame, as we had seen before. But if I now want to compare or calculate the diameter of that open sublocale, we had seen that the diameter of an open sublocale of A is simply equal to D of A, which we know is less than epsilon by virtue of the fact that A belongs to that set. The only thing that remains to show is that the join of this arbitrary collection of open sublocales gives you back the entire frame. And one can do that by simply utilizing some of the properties of open sublocales. In particular, I know that this is a cover, so therefore the join of that set is 1. But I can take open sublocales on both sides, and then I know that open sublocales preserve arbitrary joins. So because it preserves arbitrary joins, that simply means that O of 1, which is the entire frame, equals to the join of all of those open sublocales where the elements came from the cover itself. And this is how one could generate an arbitrary cover of open sublocales whose diameter is less than epsilon and whose join would give you back the entire frame. We can do a bit more than that if we now assume property S. If we assume property S, then I could do the same thing that the metric frame did, but I can now guarantee that those sublocales won't just be open, they'll be connected, but moreover, I would get out a finite number of them that we could work with. So that's the difference when we add property S. Now, Babulal had extensively studied property S star, which is actually equivalent to property S, but I'll explain. So property S star is what he had defined when he studied uniform frames. I have not defined uniform frames, and that's because I'm just going to skip through it and show you what its definition would be in metric frames. But essentially, every metric frame is a uniform frame. We could generate a uniformity on a metric frame by utilizing the cover that one gets from the metric frame, the covers that one gets from the metric frame axiom. So the definition that you see above is the definition on uniform frames by Babulal. And if we translate that from uniform frames to metric frames, all we have to do is modify what happens in covers to what happens on a metric. And the only bit that you would observe changes is that I will no longer consider a cover from the collection of covers. I would now work with epsilon greater than 0, and I would modify that condition. So this is what it now means to have property S star in a metric frame. So LD has property S star. If whenever epsilon is greater than 0, we would be able to find a finite collection of connected sublocales whose join is the entire frame, and such that this collection of sublocales is a refinement of a collection of open sublocales such that the diameter of the x's that generate the open sublocales is in fact less than epsilon. So that is what we get out in a metric frame. And that's what we're considering when we're looking at property S star. Now we can check that property S and property S star are in fact equivalent. But now, because I have this alternate formulation of property S, it means that I can do a little bit more that I wouldn't have been able to have seen before. The first of which was I tried to utilize the cover, the open sublocales that's generated here. And I wanted to say something about the diameter of the join of those things. So if you have a sublocale of your frame, such that the diameter of that sublocale is less than epsilon, and that sublocale is contained in the join of all open sublocales, which meet S non-trivially, and the diameter is less than epsilon, then the diameter of the join is going to be less than 6 epsilon. And we can check that. Utilizing this result, proposition 15, I can then prove proposition 16. And this is now well, it says the following, that property S star is equivalent to the following, that if you have any epsilon, then you can find a finite collection of connected sublocales whose join is the frame, and such that the diameter of each of those sublocales, the connected ones, are less than epsilon. And so this is moving towards the characterization that I was hoping for. And this is the characterization. So if you have a metric frame, the following would be equivalent. Your metric frame has property S, is the same as saying that for any epsilon, I can express the frame as a join of sublocales where the sublocales are open connected and the diameter of those sublocales are less than epsilon. This is equivalent to replacing those open connected sublocales by close connected sublocales. And that is then equivalent to replacing close connected or open connected sublocales by simply saying connected sublocales. So all of these formulations are equivalent, the proofs of which depended on the results that I had shown you before, because this one now follows very easily. So 1 implies 2 follows from the earlier theorem, right, to show that property S implies that the frame can be expressed as a join of open connected things whose diameter is less than epsilon for any epsilon. In order to prove that we can replace open connected sublocales by closed connected ones, it's just a matter of now utilizing closure of sublocales. And that's how we see that 2 implies 3, but also utilizing the fact that the diameter of the sublocale is equal to the diameter of the closure of the sublocale, because that's how that follows through To prove 3 implies 4, that bit is trivial to go from close connected to simply connected, to just connected, sorry. And to prove 4 implies 1, we simply utilize proposition 16 and the fact that property S star is equivalent to property S. And so that concludes what it is that I wanted to present to you today. The entire aim of today's talk was to show you that property S can be characterized in the language or in the theory of sublocales. So thank you.
Thank you very much, Cerene, for the very comprehensive talk on
Thank
these
you.
recent developments. Are there questions for Cerene?
Yeah.
There's a question at the top. And while I get there, maybe the participants online can raise their virtual hand. Here we go.
So on the slide that I think it was like 2 or 3 slides ago, where you just yeah, this one. So we were wondering, it seems like this is a very general context, and the number 6 is just appearing sort of out of nowhere. Can you maybe give some intuition as to where that comes from? It seems very like.
So what's happened here is, in order to calculate the diameter of the join of the set, I end up defining an element Z, which is simply equal to the collection. Sorry, I will define an element Z that is equal to the join of X's. So the join of X's where X intersect S, where X is in S and the diameter of X is less than epsilon. And then thereafter, once I've got the set of all of the X's in it, I will then apply the open sublocale to it, because open sublocale preserves arbitrary joins. And yeah, where does the 6 come? Okay. The 6. One moment. It escapes me now, but I do remember that this was the lower bound that I could really get, and it was important when I proved proposition 16. I'm happy to look at it and then discuss it with you afterwards as well. Yeah.
Are there other questions for Cerene? So they just asked the online people if they have questions, but nobody raised their hand yet. Any questions? Let me see if these guys have questions. And Cerene, maybe I can ask a question. I know this is beautiful, pure mathematics, but
Yes.
Are there any applications in sight at the horizon?
With metric sublocales. Well, frame theory is applicable in logic and computer science, but I haven't yet seen sublocale theory being utilized, but actually, not to give away anybody's project, but there is some work being done on chainmails that might utilize sublocale theory and have really good applications. Yeah.
Thank you. Thank you very much. One last chance to ask a question. Okay, then we forgot to mention at the very beginning that the exam will be tomorrow morning at 8 in the same room. Okay, then thank you very much. Thank you very much, Cerene, for the excellent talk. Thank you very much to all of you. And according to plan,